Scientists experimentally reconstruct Bloch wavefunction for the first time by Harrison Tassoff, University of California, Santa Barbara. In the lower right, a near IR laser separates the two electrons empty circles. Light speed is the fastest velocity in the universe, except when it isn't. Anyone who's seen a prism split white light into a rainbow has witnesses how material properties can influence the behavior of quantum objects. It is, in this case, the speed at which light propagates. Electrons also behave differently in materials that they don't do in free space, and understanding how is critical for scientists studying material properties and engineers looking to develop new technologies. An electron's wave nature is very particular, and if you want to design devices in the future that take advantage of this quantum mechanical nature, you need to know those wave functions really well, explained co-author Joe Costello at UC Santa Clara, graduate student in condensed matter physics. In a new paper, co-lead authors Costello, Simons O'Hara, and Ki Wu and their collaborators developed a method to calculate this wave nature, called a Bloch wave function, from physical measurements. This is the first time that there has been experimental reconstruction of a Bloch wave function, said senior author Mark Schwerving, a professor of condensed matter physics at UC Santa Barbara. The team's finding appears in the journal Nature, coming out more than 90 years after Felix Bloch first described the behavior of electrons in crystalline solids. Like all matter, electrons can behave as particles and waves. Their wave-like properties are described by mathematical objects called wave functions. These functions have both real and imaginary components, making them what mathematicians call complex functions. As such, the value of an electron's Bloch wave function isn't directly measurable. However, properties related to it can be directly observed. Understanding Bloch wave function is crucial to designing the devices engineers have envisioned for the future, Schwering said. The challenge has been that, because it's inevitable randomness in a material, the electrons get bombed around their wave function scatter. As O'Hara explained, this happens extremely quickly, on the order of 100 femtoseconds, less than 1 millionth of 1 millionth of a second. This has prevented researchers from getting an accurate enough measurement of the electron's wave-like properties in the material itself to reconstruct the Bloch wave function. Fortunately, Schwerving group has the right set of people with the right set of equipment to tackle this challenge. The researchers used a simple material, gallium arsenide, to conduct their experiment. All of the electrons in the material are initially stuck in bonds between Ga and S atoms. Using a low density, high frequency infrared laser, they excite electrons in the material. This extra energy frees some electrons from these bonds, making them more mobile. Each feed electrons leaves behind a positively charged hole, a bit like a bubble in water. In gallium arsenide, there are not two kinds of holes: heavy holes and light holes, which behave like particles with different masses, Sherwin explained. This slight difference was critical later on. All this time, a powerful terahertz laser was creating an oscillating electric field within the material that could accelerate these newly unfettered charges. If the mobile electrons and holes were created at the right time, they will accelerate away from each other, sloop stop, then speed towards each other and recombine. At this point, they will emit a pulse of light, called a sideband, with a characteristic energy. The sideband emission encoded information about the quantum wave functions, including their phases, or how offset the waves were from each other. Because the light and heavy holes accelerated at different rates in the terahertz laser field, their Bloch wave function acquires different quantum phases before they recombine with the electrons. As a result, their wave function interfere with each other to produce the final emission measurement by the apparatus. This interference also dictates the polarization of the final sideband, which could be circular or elliptical, even though the polarization of both lasers was linear. Is the polarization that connects the experimental data to the quantum theory, which was expounded upon by postdoctoral research Kiel Wu. Kiel's theory was only one free parameter, a real value number that connects the theory to the experimental data. So we have a very simple relation that connects the fundamental quantum mechanical theory to the real world experiment, Wu said. Kiel's parameter fully describes the Bloch wave function of the hole we create in the gallium arsenide, explained Coffee's author Seamus O'Hara, a doctoral student in the Sherwin group. The team can acquire this by measuring the sideband polarization and reconstruct the wave function, which vary based on the angle at which the hole is propagating in the crystal. Cayley's elegant theory connects the parameterized Bloch wave functions to the type of light we should be observing experimentally. The reason the Bloch wave functions are important, Sherwin added, is because for almost any calculation you want to do involving the holes, you need to know the Bloch wave function. Currently, scientists and engineers have to rely on theories with many poorly known parameters. So if we want to accurately reconstruct Bloch wave function in a variety of materials, then that will inform the design and engineering of all kinds of useful and interesting things like laser detectors and even more quantum computing architectures, Sherwin said. This achievement is the result of over a decade of work, combined with a motivated team and the right equipment. A meeting between Sherwin and Renbao Liu at the Chinese University of Hong Kong at the conference in 2019 precipitated this research project. It's not like we set out 10 years ago to measure Bloch wave functions, he said. The possibility emerges over the course of the last decade. Sherwin realized that the unique bulldizing sizes you see Santa Barbara free electron laser could provide the strong terahertz electric fields necessary to accelerate and collide the electrons and holes, while at the same time possessing a very precisely tunable frequency. The team didn't initially understand their data, and it took a while to recognize that the sideband polarization was the key to reconstructing the wave function. We scratched our heads over that for a couple of years, said Sherwin. And with Keely's help, we eventually figured out that the polarization was really telling us a lot. Now that they've validated the measurement of log wave function in a material, they are familiar with. The team is eager to apply their technique to novel materials and more exotic quasi-particles. Our hope is that we get some interest-formed groups with exciting new materials who want to learn more about the Bloch wave function, Costello said.